Okay, so let's start. Today's topic is called successive shortest path algorithm. So I just write algorithm as algo. So this is so that's to say today's topic is to introduce some algorithm that you have not learned in the class to you. Basically, this algorithm is used to solve MCF, minimum cost flow. So as I introduced last time, many problems in network flow, many problems can be transformed to minimum cost flow problem in network. So I think in the lecture you have already learned something called cycle canceling, right? Yeah. So cycle canceling. That's to say, I want to compare the difference between successive shortest path and cycle canceling. So successive shortest path. Let's see the difference. So for the cycle canceling algorithm, you know that in every iteration it maintains feasibility, and it searches for optimality. But for the successive shortest path algorithm, it is the opposite. That's to say, it maintains optimality, but search for feasibility. So that's the opposite ideology. For successive shortest path algorithm, I say that it maintains optimality. So actually later on, when I introduce this algorithm, you will see that it starts from some lower bound of the minimum cost flow, which is trivial, but it maintains optimality because it is a lower bound and it is a very loose lower bound. And then we iteratively try to find a feasible solution to it. Okay, so when we say we search for feasibility, that's to say, originally the problem is the solution is not feasible, right? What do I mean by not feasible? So originally, so because in minimum cost flow problem, we are finding some narrow flow X, right? So originally, the solution X only satisfies, don't be late next time. So originally, we have some solution X which is not feasible, but it only satisfies 0 less than or equal to xij less than or equal to uij for any ij in the arc set. This is satisfied. However, that's to say it violates the balance constraint. So remember that in a minimum cost flow problem, for every arc, we have an upper bound for the flow on it. And on every node, we have some balance constraint on it. So the balance is just outflow minus inflow should equal to something. So let's then I'll introduce some preliminaries for the successive shortest path algorithm, and then introduce the algorithm itself. So first, we look at a concept called pseudo flow. This is a concept, or say a definition, whatever. So what is a pseudo flow? A pseudo flow, actually, it is a flow X, and actually, you know that X is a function, right? It maps from the arc set to positive real number. This means that how much flow you add onto the arc ij, right? Because you are mapping from the arc set to positive real number. And as I said here, it is with 0 less than or equal to xij less than or equal to uij for any arc ij in A. However, it is not feasible due to the violation of the balance constraints. And then we also introduce it's called imbalance of a node. Let's say node I. This is also a definition. So what is the imbalance of a node I? We denote it in this way. It is called EI, which is equal to BI plus xji minus sigma j in out I xij. So let's look at it. So according to our definition, the imbalance of a node I is calculated by its balance condition plus all the inflow to I in this flow X minus all the outflow of I. So what does it mean? We know that for a balance, when we are calculating it, it means the out minus in, right? But now we are adding the real inflow minus the real outflow. So this is the imbalance. And if this is a feasible solution, then this EI should be 0, right? So EI defines how much imbalance this node has. And we can quickly get the following results. So if EI is greater than 0, what does it mean? It means that this node has some excess for I. So when EI is greater than 0, what does it mean? It means that the inflow is somehow larger, right? It is too large. So we call that it is excess. And so we use the word excess. It is just similar to that in finance. So suppose you earn more than what you should get, then you have an excess, right? And if EI is less than 0, what does it mean? It means that the outflow is somewhat too large compared with the inflow. So if EI is less than 0, we call that there is a deficit for node I. So when you see deficit, it means that you pay more than what you should pay, then it is a deficit. And if EI is just equal to 0, then the balance is satisfied. Right? Very straightforward. So this is the definitions for pseudo-flow and imbalance of a node I. All right, so now that we have defined the way to classify whether a node is excess node or deficit node, or neither excess node nor deficit node, given some pseudo-flow X. So remember that whether a node is excess or deficit or balanced depends on what pseudo-flow you add onto this network. Different flow may have different classification for a node I. Then we've already had the imbalance for node I. Then we also define two sets. Let's say E and D. So based on the letters that I'm using, E means excess, D means deficit. So E is the set, let me write down the formal definition. I in N such that EI is greater than 0. So what does it mean? Capital E means that all the excess node. And accordingly, the set of all the deficit node is I in N such that EI is less than 0. The set of the deficit node, very straightforward, right? Then we can quickly get some result. The first I want to say is sigma I in N EI equals sigma I in N BI equals to 0. And my question is why? So think about it. I claim that the summation of all the imbalance of the nodes in this network is equal to the summation of all the balance in this network, which is actually equal to 0. So can you tell me why? Please just shout it out.
Because for each EI we've got all of its inflow. We have the inflow minus the outflow of each node,
right?
And all that outflow becomes the inflow for one other node.
Yes.
So if we're adding them all together, we should have
cancel each other.
They
right?
should cancel each other out, and then you just have the sum of BI.
Right. Then why is it equal to 0?
Because the balance, besides in these problems, isn't it required that we have the sum of BI equals to 0?
Yes. So if the summation of BI is not equal to 0, then this problem no longer makes sense, right? So this is like the conservation of conservative law of energy. So in the narrow flow problem, it is the conservative law of the total flow, right? So definitely we should have the way. And according to what Thomas has just told us, that's to say, for every arc, for the flow on every arc, we included in the summation of EI exactly twice. One is in the when calculating the outflow of some node, and the other is when calculating the inflow of another node. So that's to say they cancel each other out. Okay, this is the first, and then EI. This is equal to sigma I in D EI, and this is much easier, right? Because for all the node I in the node set, EI is either greater than 0, less than 0, or just 0. So if it's 0, you can just throw it away, kick it out, or in this calculation. And then for all the remaining nodes that EI is not 0, it is either excess or deficit, and their summation is 0. So that's to say, for all the nodes in the excess set, that their summation is equal to the negative of the summation of. Okay, whatever. Seems that the network is not stable here. Okay, then what can this tell us? This is a very natural question. The summation of all the nodes in the so what does this equation tell us? It tells us that if there is an excess node, then there also exists a deficit node. Is that right? So that is to say, the excess node and deficit node, they must appear simultaneously. Otherwise, this equation is violated. So this is just like in the magnetic field. If you have north, then you must have south. You cannot just say, I only have a north, there's no south. Okay, so based on what we have said here, we can establish some lemma. Okay, so let's see, we have a lemma. And the lemma is like this. Let's say, suppose we have some pseudo flow X. It satisfies reduced cost optimality condition, reduced cost optimality condition. With respect to some node potential. So this is what we had introduced it last time. So what does it mean? X satisfies the reduced cost optimality conditions with respect to some node potential pi. So let me elaborate on this, just to do a quick review. So what does it mean? It means that Cij pi is greater than or equal to 0 for any ij, right? And how do you calculate Cij pi? And Cij pi, this is just Cij minus pi I plus pi j. So in reality, you can just represent pi as a vector such that there are as many entries as the nodes. So each entry represents the potential, the node potential of some node. In reality, pi is actually a vector. And then let vector d represent shortest path distance from some node S to all other nodes in the residual network GX. Sorry, this sentence is a little bit long, but I just copied from the textbook. With length Cij pi as length of ij. So let me just elaborate on this. So vector d represents the shortest path distance from some node S to all other nodes in the residual network. So let's just say you are given a flow, and because the flow satisfies xij larger than or equal to 0, smaller than or equal to uij. So of course you can find the corresponding residual network easily, right? And so suppose you have a residual network. Suppose this is your residual network. And D is a vector representing all the shortest path distance from some node S. Let's say this is node S to all other nodes. So you know the length of D. The length of D is just equal to the number of nodes in this network, right? And for each arc's length, it is Cij pi. So this is just a definition. And then we have the following properties. I'm sorry, I need to use this part of the whiteboard because this whiteboard is kind of small. So remember the conditions there. We have the pseudo flow X also satisfies reduced cost optimality condition with respect to pi prime equals to pi minus d. So as I have already said, pi is some vector having length as long as the number of nodes, and d is also a vector such that the length is equal to the number of nodes. So we can do a simple calculation between pi and d. We use pi minus d to be pi prime. And the first claim is that our pseudo flow X also satisfies the reduced cost optimality conditions with respect to pi prime. That's to say, i.e., Cij pi prime. This is greater than or equal to 0 for any ij. This is the first claim. And the second claim is the reduced cost Cij pi prime equals to 0 for all arcs ij in a shortest path from S to every other node. So we'll elaborate on B later. Have you already copied this? So because I want to erase it. Okay. Okay. So that's to say we want to show these two claims. Actually, to show them, it is not hard. So first, remember that I have said the flow X satisfies the reduced cost optimality condition with respect to some node potential pi. So that's to say, we have Cij pi greater than or equal to 0 for any ij. Right? This is given. This is already given in, of course, Gx, the residual network. And then, because we know that the vector d represents the shortest path distance with Cij pi as arc length. So what can we say about the vector d? D is the shortest path distance from the node S to other nodes, and the distance between ij is just Cij pi, right? Then what can we say about d? And also d should satisfy dj is less than or equal to di plus Cij pi for any ij in Gx. Is this clear? Right. Because d represents the shortest distance. So of course dj is less than or equal to di plus Cij pi. So then what can we say? So if we substitute this Cij pi, this can be substituted by, we replace it by Cij pi equals Cij minus pi I plus pi j. This is how we calculate Cij pi. If we replace this into Cij pi, then we can obtain dj is less than or equal to di plus Cij minus pi I plus pi j. And what else? What else can we say? So if we just do some simple operation to this inequality, then we can say that Cij minus pi I minus di plus pi j minus dj is greater than or equal to 0, right? We can just get this one from this one. And what does this tell us? What are these two? Pi minus d, according to our definition here, it is pi prime, right? So pi I minus di, this is just a pi prime I, and this is just a pi prime j. So Cij minus pi prime I plus pi prime j greater than or equal to 0. We can say that Cij pi prime is greater than or equal to 0, right? So if we say so that's to say we find Cij pi prime is greater than or equal to 0, then A is shown. That's to say the optimality conditions also hold with respect to pi prime equals to pi minus d. Okay, so that is for A. Okay, and then have you finished copying this? Okay. I'm sorry, I know that this part is a little bit boring, but this is arranged by Dr. Costello. She wants me to introduce these to you guys. So for B, it says that Cij pi prime equals to 0 for all the arcs ij in the shortest path from S to every other node. So let's consider a shortest path from node S to some other node L. Let's just say this is some S. Oh, let me change them to another marker. So let's consider a shortest path from some node S to some other node, let's say L. This is the shortest path. Then let's say we have I and J, they are adjacent to each other on this path from S to L. Then we must have dj equals to di plus Cij pi. Okay, quick question, why? Why dj is strictly equal to di plus Cij pi? No. Let's think about it. Very quick question.
Because if it wasn't, that means that there would be a shorter path on a different set of arcs.
Yes, very quick. So we can think about it very easily. So suppose there exists another path. That's to say, if di plus Cij pi is strictly greater than dj, then we have trouble because we can always find a shorter path to I, right? Okay, so now remember that this is strictly equal. Then, and we know that Cij pi is just Cij minus pi I plus pi j. So if we replace this Cij pi by this, we must have dj equals to di plus Cij minus pi I plus pi j. This is something that we have just talked about, right? That's to say, this is equivalent to say Cij minus pi I minus di plus pi j minus dj. What is this? This is pi prime I, right? This is pi prime j. This is equal to Cij pi prime equals to 0. Just got one step from this to this. So this is equal to 0. Then we have shown the part B. We remember that part B says that Cij pi prime equals to 0. Okay, but this is just on the shortest path. The shortest path from S to some node L, and we are discussing about Ij on this shortest path. Okay, this is for the first lemma, and we have another lemma. Another lemma. Also, let's suppose we have some pseudo flow X, and it satisfies reduced cost optimality condition. This is the assumption that we have made for the previous lemma. And reduced cost optimality condition. And also we obtain some X prime. So let me do some elaboration here. So remember at the beginning, I said that for the successive shortest path algorithm, we start from some optimal but infeasible solution. And in this case, it is just a lower bound for the minimum cost flow. So let's say you need to find some minimum cost flow to a network. Then what is a trivial lower bound? 0, right? That's to say you do nothing to the network. Then of course this is a lower bound, but because the balance constraints are not satisfied, so this is not feasible. So whenever we want to apply the successive shortest path algorithm, you can just randomly start from a 0 flow, and gradually you make adjustments to it until it becomes a feasible solution. This is the ideology of successive shortest path algorithm. So this lemma tells us that suppose you have some flow X that already satisfies the reduced cost optimality condition. So think about this. In the zero flow, does it satisfy this? Yes, right? And then we can obtain X prime in some way. So that's the reason why we introduced the lemma here. It tells you how to iteratively update some narrow flow until you get an optimal, a feasible solution. So this tells us we can obtain X prime from X by sending flow along a shortest path from S to some other node K. Then, so what does it tell us? We can make adjustments to the pseudo flow X by sending a flow along a shortest path from S to some other node K. So S to some other node K. We can send flow from S to K. And then X prime also satisfies reduced cost optimality condition. So remember that I said for successive shortest path algorithm, you maintain the optimality, but you iteratively search for a feasible solution. Here, when I say optimality, what do I mean? The optimality means the reduced cost optimality condition. That's to say, in every iteration, you are adjusting this flow X. However, you should always make sure that it satisfies the reduced cost optimality condition. And once this solution X, once the flow that you currently have satisfies the feasibility condition. Now, what can you say? It satisfies the feasibility condition. That's to say, satisfies the balance constraints. And also it satisfies the reduced cost optimality condition. Then this is a feasible and also optimal solution. Then you are done, right? This is the ideology. So this lemma tells us that if you send a flow along a shortest path from S to some other node K, then now you have changed from X to X prime. The claim is that X prime also satisfies the reduced cost optimality condition. Right. So what is so how can we prove this? The proof. Let's first define node potentials pi and pi prime as we did before. That's to say, initially you initialize some node potential pi, and you calculate the node potential pi prime as we have just introduced. Then you first you define the node potentials. Then by the previous lemma, what can you say? We have some node S, we have some node K, and this is the shortest path from S to K with arc length Cij pi, right? And on this path, let's say you have I, you have J. Then we can say that Cij pi prime is equal to 0. This is what we have shown in part B of the previous lemma, right? Cij pi equals to 0. This is the shortest path. This is the shortest path from S to K. And by the previous lemma, we can say that Cij pi prime equals to 0. And then if we augment flow on any such arc, might add its reversal Ji to the residual network. So what does it mean? Let me write it down. We augmenting flow on arc ij might add its reversal to residual network, right? This is very straightforward. That's to say, if you want to augment some flow, and suppose originally the flow on this arc is 0, then after you augment flow on this arc, you must add its reversal to the residual network. This is very clear, right? However, since Cij pi prime equals to 0 for each ij on the path from S to K. So that's to say for any arc ij on this shortest path from S to K, we must have Cij pi prime equals to 0. And also, the arc Ji also satisfies the reduced cost optimality condition. So let me elaborate on this. So we see that Cij pi prime equals to 0 for any ij on this shortest path. And the arc Ji, I mean in the residual network, also satisfies the reduced cost optimality condition, because it's just the opposite. It's just the opposite and it's 0. So the opposite is also. So that's to say, Ji should also satisfy the reduced cost optimality condition, because equals to 0 is definitely greater than or equal to 0. Equals to 0 implies greater than or equal to 0. So the optimality condition is also satisfied. Then recall that what we're doing in this lemma. We say that x prime also satisfies the reduced cost optimality condition. That's to say, let me elaborate more on this. So that's to say, now you have some flow x, right? And you augment some flow. You have a flow x and you augment flow. How do you determine which path do you augment this flow? It is on the shortest path, right? From S to some other node. You augment flow along this shortest path, and this tells you that you get x prime. This tells you that in x prime, the reduced cost optimality condition is also satisfied. So this lemma guarantees that whenever you augment flow in this manner, you still get some flow x prime, which satisfies the reduced cost optimality condition. That's why we want to talk about this lemma. Is that clear? Okay. If we augment flow in this manner, it also satisfies the optimality. Okay. Another question. How can you find the shortest path from some pre-specified node S? This node S can be just any node in this network, whatever. How can you find the shortest distance from S to any other node? Think about what you have learned in this course. How can you find the shortest path from S to any other node?
Like the label breaking algorithm?
You mean Dijkstra?
Probably.
Yeah. So you can just use Dijkstra algorithm. I know that you have learned something called, say, label correcting algorithm, but if you just look at those programming websites, they just call it Dijkstra algorithm, right? So Dijkstra algorithm is used to solve single source shortest path algorithm, single source shortest path problem. And because now we don't have negative arc, so you can just use Dijkstra. But if you have negative arc, what should you do? Single source shortest path, but with negative arc. What's the algorithm that is used to solve single source shortest path, but with negative arc? named by two persons. Bellman, Ford. Yes, Bellman, Ford. Right. So this is how to say. Actually, in this course, you will learn some theorems, but actually, if you want to really implement these algorithms, they are much trouble. You always need to recall how to solve some problems. For example, here, we are assuming that you can find a single source and shortest path, but if you want to implement it, you must implement Dijkstra algorithm a priori, right? Okay, so this tells us that if you augment a flow on such arc, you obtain X prime, and X prime also satisfies the reduced cost optimality condition. So this so by this we can quickly talk about the algorithm, and then we can finish today's section. Okay, so the algo successive shortest path. Successive shortest path. Then, as I have just said, you start from some flow, which is trivially the lower bound. So you can just initialize x equals to 0 and pi equals to 0. Then in this case, this is trivial. But it has already satisfies the reduced cost optimality condition. That's Cij pi greater than or equal to 0 for any ij, right? This is a trivial solution. Then our objective is to obtain some flow such that it also satisfies the balance constraint. Okay, so we initialize x equals to 0, pi equals to 0. This is the trivial solution. And in this case, the imbalance of node I is just a bi, right? Because currently there's no flow on this network. Then the imbalance of node I is just equal to bi for any I in the node. And how do we initialize? And we also initialize E and D. So we know that initially EI equals to BI, and for BI, we know that some will be positive, some will be negative, and the summation of BI equals to 0, right? So there must be, so that's to say, the excess node set and deficit node set should both be non-empty, right? If they are empty, if one of them is empty, the other one must also be empty. That's to say, all the BI equals to 0, then there's nothing to do. The trivial solution is already the optimal solution. Then there's nothing to do. So we initialize ED, and we are pretty sure that they are both not empty set. Okay, then we use a while loop while E does not equal to 5. That's to say, whenever there is some element in E, or in other words in D, then you should iteratively update. Okay, we select the node K in the excess node. That's to say we select some excess node, and let's say we select L in D. That's to say we pick an excess node, and we also pick a deficit node. Then we determine dj from node S to all other nodes J in the residual network with respect to Cij pi. So initially, because we don't have any flow on the network, then the residual network is just the original network, right? And we determine dj from node S, and node S is just just any node in this network. You can just naively set it to be say node 1. this step tells us that you need to determine the shortest distance, dj, from say node 1 to all other nodes in this network with respect to Cij pi. And pi is given. Initially it is 0. So Cij pi initially is just Cij, the cost on each arc. And then we let P denote shortest path from K to L. Then what can we quickly say? We have already established the shortest path distance from some node S to any other node, right? Let's say S is some center. And we have already had the shortest distance from S to any other node. Then we let P denote the shortest path from K to L. Remember, K is some excess node and L is some descent node. What can we quickly say? This shortest path must be on the shortest path from S to L, right? Let's just say in the shortest path, you have shortest path from S to L, and K must be intermediately, right? Otherwise, this is not shortest path distance. Okay. And remember that because we are using Cij pi as the arc length, then we must have Cij, and we have said that it satisfies the reduced cost optimality condition. Then Cij pi must be greater than or equal to 0, and that's the reason why we can use Dijkstra algorithm. Because we don't have negative arc length, so we don't need to use Bellman-Ford. You know that Dijkstra has a lower time complexity than Bellman-Ford. Okay, so we let P denote shortest path from K to L, and we update pi equals to pi minus d. So previously, when we introduced the lemma, we say that pi prime equals to pi minus d. But now you can just feel free to update the node potential pi equals to pi equal minus d. And we let delta equals the minimum of Ek minus El and minimum of this step is kind of complicated. I'll explain why. So Ek, we know that K is excess, so Ek is greater than 0. And L is deficit, so El is negative, so we take the negative of El is positive. And the minimum of Rij, R is the residual for any Ij in this shortest path from K to L. So what is delta? Delta means how much you can augment along this path, right? It is minimum means that, so that's to say for every arc in this in this path from K to L, the amount of flows that you can augment are different. So you take the minimum. This is the amount of flows that you can augment through this path, right? This is what you can augment through this path. And then we augment delta along the path P. And we do some update to X, Gx, E, and D, and reduce the costs. Iteratively until there's no excess node and there's no deficit node. This is the algorithm of successive shortest path. So I think that's the end of today's section. If you have any question with respect to this algorithm, just feel free to ask. And on your textbook, section, if I remember clearly, it is section 9.7. There's an example. So I know that this might be kind of confusing at first. So if you look, you can just go to section 9.7 and look at the example, and I think you will be clearer about what the hell it is doing in this this algorithm. But I think I have already told you clearly why we use that two lemmas. What's the meaning of that two lemmas? So key takeaways. What do we mean by satisfy optimality condition? The optimality condition is the reduced cost optimality condition. Cij pi always greater than or equal to 0. And because Cij pi is greater than or equal to 0, and we treat it as the arc length when defining the single source shortest path distance, then we can always use the Dijkstra algorithm. And we can make sure that whenever we update this pseudo flow X, the optimality condition is not violated. Then, as long as you can make excess node set and deficit node set to be empty at the end, you are done. If E, D are both empty, then that's to say all the balance constraints are satisfied. All the balance constraints are satisfied. That's to say the feasibility condition satisfied. And optimality condition satisfies, balance condition satisfies. Then this is a feasible and optimal solution, and you are done. Is that clear? Okay, I can stop recording now.